Hello and welcome. For this video we are going to talk about the different types of nuclear radiation that you can have and the features and characteristics of those three different types of nuclear radiation. Now, to begin with, we've got an example of an atom from an element. This element is radioactive. Two examples are uranium and plutonium, and these are ones that are often talked about for your GCSE physics. And it's important to remember that when we talk about radioactivity or nuclear radiation, it's radiation that's coming from the nucleus of the atom. So while I've got a whole atom here with all the shells, I haven't drawn any electrons in, but there would be electrons there for this atom. While we've got all those structures for an atom, it's only the nucleus that we really focus on when we're talking about radioactivity or nuclear radiation. So I'm going to get rid of all of these electron shells and we're just going to focus on the nucleus. So here we have it, a radioactive nucleus. Now if this is radioactive, it's going to be able to give out one of three different kinds of radiation. Now the first one is called alpha radiation, and this has a very special makeup or a very special structure. So if this nucleus here was to give out a particle of alpha radiation, it would look a bit like this. It's also important to remember we don't know when, or we can't predict when this is going to give out some nuclear radiation because it's a spontaneous and random action, meaning we can't predict when it's going to happen and which atom is going to happen in. But imagine this is given out one particle of alpha radiation. That particle looks like this. Okay, so what I've got here are two protons, so the protons have a positive charge, and two neutrons which have no charge. So this gives this particle an overall charge of 2 plus. In actual fact, if you were to look at the nucleus of a helium atom, this would actually be would look exactly like this. So this is actually a helium nucleus. It's also an alpha particle. Okay, so there are some certain characteristics that you need to know about this, and we'll summarize that momentarily so that you can see a bit more clearly. But that's one type of nuclear radiation that can be given out. The second type is called a beta particle, and that is basically an electron. So this is a beta particle, and that is basically an electron that is ejected from the nucleus. Now you might think, hold on a minute, electrons don't actually exist in the nucleus, they are actually in the shells along or around the nucleus, but there is a certain process that happens where a neutron is broken down into a proton and an electron, and that electron is ejected from the nucleus as a beta particle. And because it's a beta particle and because it's an electron, it has a little negative charge. The third type of radiation that can come from the nucleus is called gamma rays or gamma radiation, and that is actually an electromagnetic wave. So it has no mass, no charge, and it is emitted from the nucleus of a radioactive element. So we have our table here to summarize the different features of these different types of particle, and in this table we have alpha particle, beta, and gamma ray. Remember, the gamma ray is an electromagnetic wave, the beta particle is an electron, and the alpha particle is a helium nucleus, or two protons and two neutrons. Now what is this made up of? Well, we've just said that. We said it's two protons and two neutrons. The charge on it, because we have two pluses and two neutrals, is 2 plus, and the mass is 4, because there are 4 of these particles each having a mass of 1, which you may remember from a previous video. The mass is 4. For a beta particle, it's made up of an electron, has a charge of -1, and the mass is tiny, too tiny to really measure. For a gamma ray, it's made up of an electromagnetic wave. It has no charge and no mass. Okay, and you should be aware of these key features about these three types of radiation. Okay, so the next thing I want to look at is how far they can penetrate in air and what they can be absorbed and stopped by. And again, this is something that you have to remember. It's not hugely difficult, but it's just something that you might have to go over to remember it. So for our alpha particle, the range in air is a few centimeters. Sometimes it may be up to 5 or 10 centimeters, not much further. For a beta particle, it can go up to about a meter, and for a gamma ray, well, this can go actually quite a long distance. Some books say many kilometers. I've actually seen it written as unlimited through air. but the key point is it can go very, very far in the air if it's not blocked by anything. For our alpha particle, it can be stopped or absorbed by just a layer of paper. In actual fact, your skin can stop it as well. So if you have alpha particles, if you're near alpha particles or exposed to alpha particles, your skin will actually absorb and stop those from getting into your body. In terms of a beta particle over here, this can be stopped by a few millimeters of aluminium. And for our gamma rays, well, this takes much more effort to absorb it or to stop it, and this will take a few centimeters thickness of lead or a few feet of concrete. There you go, that's a bit tidier. So we're talking a few centimeters of lead for our gamma rays, maybe 5+ centimeters, and maybe over a meter for concrete. Okay, so this is just basically, unfortunately, stuff you have to remember, and make sure you're able to answer any questions that might be related to the features of these three types of radiation. The last thing I want to look at is the deflection of these types of radiation in electric fields and magnetic fields. So here I have a source of radioactivity. Here's an electric field. We've got a positive plate and a negative plate. These are created by connecting to a source of electricity, and if we were to fire a alpha particle through this field, what would happen is that would be attracted by the negative plate. Alpha particles are positive, so it would be deflected towards the negative plate. Okay, so that's because of the attraction. If you were to draw the pathway, it might look a little something like this, and you can see the attraction causes a little bit of deflection. For a beta particle, which is an electron, that would be deflected much more, and even though the charge is smaller, this has a charge of -1, this has a charge of +2, even though the charge is smaller, because the mass is tiny compared to the mass of our alpha particle, it's going to be deflected a lot more. So our pathway might look a bit more like this. Much more deflection compared to an alpha particle. Now, in terms of our gamma ray, there is absolutely no mass to it and no charge, so there will be no deflection of our gamma ray. For our alpha particle, there would be more deflection, but not as much as our beta particle. In terms of our magnetic field, the pattern is similar. There is most deflection of beta particles, less deflection of alpha particles, but in the opposite direction to beta, and for gamma rays there is no deflection. Okay, so lots of stuff basically just to remember really in this video, but you do need to know it, and you should be able to use this information to respond to any questions that you might be given. So thanks for watching, and I'll see you again soon.